We're going to finish up this unit on context-free languages today by kind of doing a little bridge over to the next stage, which talks about Turing machines and unrestricted methods of computation. And the bridge is going to be talking about decidability of questions about context-free languages. And basically, you can't decide too much about context-free languages. You can decide a little bit about deterministic context-free languages. You can decide almost everything about finite-state machines and almost nothing about Turing machines. So there's a hierarchy, and the ability to decide questions about them gets harder and harder as you go out from the center toward the fringe. The way you prove that a problem is undecidable, at least originally, is to use that barber who shaves everybody in town except himself trick. Use the diagonalization trick. I'm leaving that for a completely separate day when we talk about Turing machines, because it needs a separate day, it needs a separate review. You need to be completely clear and not have anything else on your mind. And then we'll do the first undecidable problem, which is basically the question of whether a program goes into an infinite loop or not. That's impossible to decide. It's impossible to write a program that takes another program and tells you, will this ever infinite loop or not, yes or no. Can't get that right. You can prove that with diagonalization. Now from there, you don't want to bring out your diagonalization hammer again. You'd rather leave it in the closet and just relate that to other problems with reductions, to kind of show a relationship between other problems and the problem of whether you can tell whether a program infinite loops. The hard thing is to get that relationship to switch from checking programs for infinite loops to checking very practical things about grammars, like whether grammars are ambiguous, whether two grammars have any strings that they generate in common, whether the complement of a grammar that's context-free is also context-free. All those things are undecidable, but there's no obvious connection between them and checking whether programs have infinite loops. So the bridge between undecidable questions about computer programs and undecidable questions about context-free languages is done through this famous problem called post-correspondence problem. And we did this yesterday, and I want to review what it is, remind you what it is, and I will tell you, and you have to take this on faith right now because it's a very technical and long proof, that somebody has proved that if you could solve the post-correspondence problem and decide yes or no to instances of the post-correspondence problem, then you could also figure out whether a program infinite looped or not. A solution to this would imply a solution to that first famous undecidable problem, and therefore no one's ever going to come up with a solution to this either. That's what a reduction is. Somebody has reduced the infinite loop problem, the halting problem, to the post-correspondence problem. It's a very technical reduction that takes Turing machines and converts them to pairs of strings. It's not what we're going to do today at all. Just take my word for that reduction. But because it exists, we know that the post-correspondence problem is undecidable, and it's this which is going to give us a link to all the other questions about context-free languages, and the reductions there will be very straightforward, not trivial, but at least handleable and understandable in one day. Okay, questions? Yeah.
What meaning does the word post have here?
It's a guy's name.
I was trying to make it like your name or something.
Yeah, Emil Post, I think was his name. Yeah, when I heard this, because correspondence, right? You think it's like some old British, mail networking problem. Charles Babbage figuring out that it's good to charge just 5 cents for a letter instead of 6 cents if it's going 100 miles further or something. No, it's his correspondence problem. Post had another problem that Michael Sipser mentioned in his lecture, which was a famous unsolved problem in recursive function theory, which was recently solved by some clever 18-year-old who then decided not to go into math and computer science, but what did he say he did? Became a lawyer or a doctor? MD, a doctor. So I'm sure his parents are proud. And
now, unlike all of the reductions, the P and P reductions we did, where we still don't know whether P equals NP, this, we've proved, so all of these reductions...
Yes, these reductions are useful. Well, they're all negative results in some ways, in the sense that when you make a reduction from the halting problem to the post-correspondence problem, you do actually prove that the post-correspondence problem is impossible to solve. It's not... Well, you're showing that if the halting problem was impossible to solve, then so would this one be. Or on the other hand, if you were able to solve the halting problem, then you could solve this one too. But we know you can't solve the halting problem. That's very well known. That's the diagonalization proof. That's Cantor's idea, breathed into computer science, and it's definitely can't be done. Therefore, this definitely can't be done, and everything else we're going to reduce from this today won't be able to be done at all. No programs ever to do them. So these are negative results. It's bad that you can't do all these things, but it's important to know that you can't do them so you don't spend any time trying to do them. And so that you spend time trying to do at least the approximation of things that might help you to handle the things that you can't actually do. So let's look at this problem so everybody knows what it is. Here's what you get in the post-correspondence problem. You get a list of strings that come in pairs. One from column A, one from column B. And the list can be very long. In this case, I just made a list of 3, but it's arbitrarily long how long the list is. And you're given this list, and the question is, can you take a sequence of these numbers so that when you connect all the A's in that sequence, you get the same string as when you connect the B's in that sequence? Okay? So for example, let's try to take the sequence 1, 1, 2. That would give us a 1, and a 1, 0, 1, 1, 1. A 1, and a 2 would give us 1, 1, 1, 1, 1, 1, 1, 0. And do they match? No, they don't match. So that doesn't work. The sequence 1, 1, 2 doesn't give us a match of the A column and the B column. Okay? So here's one instance, one input to the post-correspondence problem. Here's another input. I put 2 of these up because I want you to at least get a sense of what it feels like to try to solve the post-correspondence problem. There's no algorithm that does it, but you as human beings can stare at these 2 particular instances and try to solve it anyway. The fact that there's no algorithm doesn't mean that we can't solve a particular instance. We might be able to. It's just that you can't write a general set of rules that's going to solve all of them, even though you might figure out the secret behind each of these.
The question is, does every setup match?
No. Is there one setup that makes the A's and the B's match up?
Oh, just one.
Just one. If you can find one, the answer is yes. If you can't find any, the answer is no. Yeah, Joe?
Use all the strings?
No. No. For example, if A and B both had the same string, on either side, then you'd be done right away. You just pick that one string, you're finished. Okay? So it doesn't have to use all the strings. And you can use a string more than once.
Well, where did this come from, this problem? Why would anybody make this up?
Well, the halting problem is kind of technical and hard to make reductions from. Because to make reductions from it, you have to take an arbitrary Turing machine and convert it to a grammar. That's hard to do, and it's a little ugly. And even when you do it, it's technical. But this is simple and pure and distills the undecidability of the halting problem down to its kind of elemental bare bones. And because we have it in such a simple way, I'm going to be able to describe reductions to you that immediately imply that all these interesting questions about grammars are hard to do, specifically because I have this starting point. So the scientists here were looking for something simple like this. They were hoping, because they knew that if they got something like this, they could branch over to context-free grammars. So they're looking for it. So they look at the Turing machine and see, how could I distill it down to something like this? This looks like it's hard. There's variations of this problem, by the way, that aren't hard. Like, if I have it over just one symbol instead of ones and zeros, just zeros for all the strings. Everyone understand that variation? So just zeros. Basically, you have a number on each side. That you can definitely solve. That's decidable.
So, I'm sorry.
Yeah?
The goal again is to come up with a string of ones and zeros.
No. A sequence of these numbers.
A sequence of what are the numbers?
1, 2, and 3.
Okay. Oh, the rows. Row numbers.
A sequence of rows so that when you connect the A's together, they equal what you get when you connect the B's together. And you just have to find one such sequence. All right, so I'm throwing it to you just to get you warmed up a little. Which one of these is the answer yes? Which is the answer no? If the answer is yes, can you show me how to solve it? If the answer is no, can you give me some explanation why you think the answer is no? And I'll give you a hint. One of them the answer is yes, one of them the answer is no, and for the one that the answer is no, you can definitely give me a logical explanation as to why there's no way you'll ever get it. You have to think about that because there are, after all, an infinite number of sequences to try, so whatever argument you give me, it has to work for every sequence. If you're going to show me that there is a solution, you just have to give me one sequence. That's a little easier. So I don't know, spend a couple minutes playing with it, and I'll tell you the answer if you don't find it. I don't think there's any special cleverness to being able to find it. If you happen to see it, that's fine. Should we look at this one together first, maybe a little bit? Let's think out loud with this one. If we were to try to get it, Joe, you have an idea?
And I just have a question.
Yeah.
The string lengths don't have to be the same size. Like you don't need the same number of rows on one side as the other either, right?
Yeah, you do.
Yeah, when you pick, say, 1, 2, 3, you're getting this all concatenated together, and this all concatenated together, and the sum of all those symbols has to be the same to match. Yeah, definitely.
Okay.
Well, then isn't that the problem with the first one?
Here?
Since their lengths are different, there's no... Well, I guess there's some combination you could...
I might be able to combine these so that the sum of these might equal the sum of these. I might.
Length.
It's certainly a good place to look for. I mean, if the lengths of the left is always smaller than the lengths of the right, then there's no way to do it, because the left side always has a string that's smaller than the right side. You can't get a match. So there's got to be at least one on the left that's bigger than its pair on the right, and one on the right that's bigger than its pair on the left. Otherwise, you have no chance. But all of them satisfy that, so that's not going to help us. Let's look here for a second. If there were a sequence to solve this problem, what would it have to start with? Which one of the numbers, 1, 2, or 3? 1. Right, 2 and 3 immediately get mismatches. The 0 and the 1 and the 0 don't match, so it's got to start with 1. Let me write down a potential solution here. So 1, 0, here's our sequence 1. 1, 0, 1, 0, 1. Here's the A, here's the B. Okay, fine. So what's next? Can I continue?
It's got to be 1 or 2. And it's got to be 1.
3.
It can't be 2, right? Because 2 would have the 0, 1, 1 showing up here, and that wouldn't match. So that's out right away. Can it be the 1?
No, because the 1 in front of the B would...
What would happen? What's the problem with this one? We'd have a 1, 0 here, and we'd have a 1, 0, 1 here, and that's a mismatch. So we can't continue with the 1. Well, so maybe we continue with the 3. Let's try. So this becomes 1, 0, 1, and this becomes 0, 1, 1. That looks very similar to what we had just about 10 seconds ago. We had a string that was exactly identical, but this one had an extra 1. And the same argument we used before about how to continue is going to apply now. Can we continue with a 2? No, because it mismatches. The 0 mismatches the 1. Can we continue with a 1? We could try. We'd get a 1, 0 on the top, and then a 1, 0, 1 on the bottom, which would this one would mismatch with that 0. So we can only continue with 3. Well, that's great. Same argument again. We can only continue with 3. We can only continue with 3. The only way we can possibly have a chance to match these strings up is continuing with string 3. 1, 3, 3, 3, dot, dot, dot. And none of these ever even out. You always have the bottom being a little bit longer than the top.
Can you buy a vowel?
We can buy a vowel. Yeah, that'd be great. Vanna White starring in the Post-Correspondence game. It's an undecidable question, but here we give away prizes for solving exactly that. Well, I don't know. I was never any good at math. Buy a vowel indeed. Yes, well, we can't do this one. That one's right out. The answer is no. So now maybe you go back and think of writing a program, that looks for things like this. a program that checks for these logical inconsistencies. Maybe there's a way to completely encompass all the logical things that could go wrong, but there isn't. That's the nature of undecidability. There are essentially an infinite number of different things you would have to check for. There is nothing finite that describes all the possible reasons why the answer here is no. That's really what undecidability means. There's no finite way to describe all the things you want to check for. If I want to accept all the strings of 0, star 1, that's a nice finite way of describing an infinite number of things. But there's no finite way to describe all the infinite pairs of things that don't have a solution to the post-correspondence problem.
So you're saying you can do the first one?
I'm saying you can do the first one. Yes, you can definitely solve this one. Anybody want to try? 2113? Well, using the general tenet that Erica's always right, she says 2113. Well, is it right or wrong? Let's write it out. 2113 gives us what string for A? 10, 111. Then 2 1s give us 2 1s. And 13 gives us 10. That's 2113 for A. And what about for B? 10, 111, 111, 0. 10, 111, 111, 0. And that's fine because Erica, because she's a human, does have a post-correspondence problem solution embedded somewhere in her organic makeup, and she just solves these things. I don't know how she got that, but that's right. That's a solution. How could you write a program to do what Erica just did? If there were an answer to guarantee you would find it, how would you do it? No, you could find it if there was an answer.
And 6 strings, you could just, I mean, likely get to a point where you could sense that there was no way to go other than repetition.
Well, I'm not looking for a way to know that the answer is no, because there isn't any way.
Right.
I'm looking for a way just to make sure that if the answer happens to be yes, that we find it.
Yeah, you can just
Try
start
all
trying.
combinations.
Yeah, so let's be specific. We always say stuff like that. Oh, just do it by brute force, you know. And I can't remember how many times when I was told that I thought, yeah, I'm glad you're not telling me to do it because I'm not quite sure how to do it. So in this case, it isn't too hard. But let's say what we specifically mean by trying it by brute force. Let's try all the sequences that have length 1. Here they are. Okay? Just 1. That doesn't work, that doesn't work, that doesn't work. Okay, let's go on to the sequences of length 2. How many are there? There's 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, right? So there's 3 of the sequences of length 1, 9 sequences of length 2. How many sequences of length 3? No, I think it's 3. 3 to the 1, 3 squared, 3 cubed, so it's 27. And then there's 81 sequences of length 4, because you got 4 spots and 3 choices for each spot. So that's probably how Erica did it. She went through all the 81 sequences of length 4, and one of them worked. No, she didn't do it that way, but that's how a machine would do it, right? And a machine could definitely do that. You could have the machine generate these sequences, check them by concatenating the strings, and if it ever finds that the 2 are equal, it would stop and say yes. And that's not an algorithm or a decision algorithm because it could easily run forever and never tell you no. That algorithm never says no. It just says yes when the answer is yes. If the answer is no, it just runs forever. That's why sometimes when we think of a problem as undecidable, we think of one half of it being kind of partially decidable. Okay, undecidable doesn't mean you can't answer both sides of the question. It just means you might be able to answer one side of the question, but that's not very interesting. Because if the answer is the other side, you'll be sitting there forever. Okay, so that's a review of the post-correspondence problem. Are there questions about this? So this one's got a solution, this one doesn't. No algorithm anybody knows that is possible to solve it in general. What we're going to do now is connect this to questions about context-free languages and review what questions we know can be decided for context-free languages and try to prove that some of the others really can't be, instead of me just telling you that they can't be. Okay, here's one question. Context-free language, does it equal the empty set? Somebody gives you a grammar, they want to know, does it generate something or absolutely nothing? Can you decide that or not?
Turn it into the Chomsky normal form.
You can turn it into the Chomsky normal form and see if S is a useless symbol. Right. Perfectly reasonable way to do it. So this is decidable. It's one of the few things that's decidable about context-free language. Okay, I'm going to put, just to contrast, DCFLs over here. Somebody gives you a DCFL and wants to know if it's empty or not. Is that decidable or undecidable?
Decidable.
Yeah, how come?
Well, all of those are those.
Okay. All right, so I just do the same thing. I take it and I check if the start symbol is useful or not. Okay, so that's decidable. Right, all of those are those. What about this problem? The language equals everything. It generates absolutely everything. Let's do it first for DCFLs. Is it hard or easy to check if the language generates everything for DCFLs? Can you do it or not?
Can you minimize the DCFL?
No. Too bad. Be nice. Now, there's no minimum pushdown machine or anything like that. You can think about things like that. You can ask yourself, what's the minimum number of stack symbols I need to use, or the minimum number of states, and try to make some kind of theorems about that, but there aren't very many useful ones. Well, I'll give you a hint. The answer is that you can definitely do it. And it's not so hard. When I tell you how, you'll say, oh. It relates to a closure property. What are DCFLs closed under? They're closed under complement, right? So if I give you a machine and I want to know if it accepts everything, you could just take the complement of the machine, that's also a DCFL, and check if that accepts nothing. If it accepts nothing, then the original accepts everything. So this is definitely decidable, and in parentheses, because of closure of complement. But if you try to do that same trick for regular context-free languages, it fails, because when you take the complement, you don't necessarily get another context-free language. So asking whether a context-sensitive language or a more unrestricted grammar is equal to nothing, that's undecidable. So if you take a language and you take its complement and it knocks you out of the context-free languages up higher up, and then you're hoping to check whether that's empty in order to determine whether the original was everything, you're dead in the water, because checking whether Turing machines or unrestricted grammars accept nothing, that's hard to do. And in fact, doing this is hard to do. There's no way around it. And I'm going to show this to you. I'm going to prove to you today that checking whether a given CFL accepts everything is undecidable.
Is the complement of a deterministic one, can you get that the same way you can for finite state machines?
Yes, modulo some stupid technicalities. If you actually try to do it, you'll find some little details that show up, and you'll say, why didn't Shai tell me about that? And it's because I didn't feel like it. There are some dumb technicalities involved, but essentially it's the same proof with finite state machines. Essentially, the non-final states become final states, and the final states become non-final states. And since it's deterministic, everything works out just fine. Essentially, it's the same proof. Okay, here's some other questions. Take two languages, L1 and L2. You want to know if they have anything in common. Are they completely distinct, or do they have something in common? Is there something in their intersection or not? That's undecidable for context-free languages. And in fact, I think it's also undecidable for deterministic context-free language. I'm pretty sure. I'm going to check. It's probably in our list. Yes, it is. So sometimes there's a distinction between deterministic context-free and context-free, and sometimes there's not. Here's a question. If I give you a language and I take its complement, I'd like to know, is that context-free or not? If I was able to know that, I might be able to make better use out of my trick over here. Somebody gives me a language, is its complement context-free or not? Context-free language, is its complement context-free? Sometimes it will be, sometimes it won't be. To determine that yes or no is undecidable for context-free languages. What if I gave you a deterministic context-free language and I ask you, is its complement deterministic context-free? What's your answer? Yes. Your answer is yes. So there's definitely an algorithm that says that. It's the algorithm that says, print line yes, or whatever your language does to print the word yes. So we say that this is trivial, which means decidable. So some of these problems are just trivial, and some are decidable, and they're a little harder. Here's a good one. Somebody gives you two languages, and they want to know if they're the same. Now, this is not just some stupid esoteric question about grammars. Somebody in one company builds a compiler for the ANSI standard of Java, or whatever there's an ANSI standard for nowadays, and some other companies also building a competing compiler, and everybody wants to know, do they really do the same thing? Do they generate the exact same language? Are they both Java compilers? And the answer is, you can't send it to the equality checking, VeriSign compiler checking company that will tell you if they're really the same. There's no algorithm that does that. So you can't check in general whether two compilers really accept the same language. Some particular two you might be able to check, but not two in general. So undecidable.
You can't check if two chips are identical either. Intel versus
That's a little trickier, but generally not. Right.
Why would it be tricky?
Because chips don't always necessarily generate things as complicated as context-free languages. There are chips that are just finite state machines, and then you could. Right? So for complex enough circuits, the answer would be it's undecidable. Mm-hmm.
Backing up just a couple to the question of whether two languages share anything in common.
Yeah.
Could you just mention why that's undecidable?
Oh, you mean like why? I haven't proved that any of these are really undecidable yet. You mean why intuitively it's hard to do this?
Yeah.
How would you try to do this? What would you do? You could try every string and check membership in one language and check its membership in the other language. There is a decision algorithm for doing membership. So you check, and you check them, say, in size order. First we'll check the empty string, then we'll check 0, then 1, then 0, 0, then 0, 1, then 1, 0, then 1, 1, etc. We'll check all the strings in the whole world in size order. And we'll check each one in both these languages. And if any one is accepted by both languages, we'll stop and we'll say yes. And that's true. If the answer to this is that they have something in common, we'll be able to stop and say yes. But what if they have nothing in common? We're going to just go through this forever and ever and ever and ever. We'll never find one string that's in both, and we'll just have the person who typed in the question waiting and waiting for an answer. And they won't find out whether it's yes or no. Does that give you some intuition as to why it's hard? It doesn't mean it's really hard. That's just the only way I can think of doing it, and it's not a good way. Wow.
L1 equals L2, there's a question mark for.
Yeah. And we're up to that right now. Good point, Michael. L1 equals L2. I give you two deterministic context-free languages. Do they generate the same language? This is really the question about compilers, right? Because compilers are all deterministic context-free languages. They're not really non-deterministic. They're all in that world. So this is a very important question. An automatic compiler equality checker. That would be nice. So as of the publication of this book, which was 1980, this problem was still unknown. Nobody knows how to do it. Nobody knows whether it's undecidable. And I don't know, and I don't think that there's been any resolution of this. So nobody knows. If you figure it out, and assuming it hasn't been solved in the last few years, you will be famous. What if these two were finite state machines? Is it decidable or undecidable? Decidable, because you minimize them and you test them for identicalness and you're done. So DCFLs are kind of in this funny never-never land of right in between finite state machines and context-free languages, and have some of the decidable properties of each. Not terrible, in the realm of being able to work with them, but still not as nice as finite state machines.
And is the equals not true for the same reason you have to check every possible string that can be generated in a language? There's no way to compare the machines.
Right. I don't want to say that's why it's undecidable. That's not why it's undecidable. That's a justification for why I believe it's undecidable, because any way I try to do it seems to run forever. Right. How would we try to do this? We'd try to take every single string and check them for membership in each of these languages and hope that the membership answers match. You know, that yes goes with yes and no's goes with no. And if we ever get a mismatch, we'd stop and we'd say these languages aren't the same. But if the languages are the same, we'll never know it.
But I might also think there's some way to compare the machines.
Oh yeah, right.
Grammar.
And in fact, people do think that for deterministic context-free languages because nobody knows.
So there's some proof that's...
Oh yeah, no, I'm going to prove to you that you can't do this. Okay. Yeah, we're in 10 minutes. We're going to, every one of these is all undecidable. I'm going to convince you. And it's not going to be some weird, twisted, who knows what's going on proof. It's going to be very straightforward and very constructive. As long as you believe that this is impossible to do, I'm going to convince you that all of these things are impossible to do. And it's through this idea of a reduction. All right, questions? So let's do it. Let's do some of them at least. Okay, what's a good one to start with? How about, we'll start with this one. We'll start with trying to find out whether the intersection of any two context-free languages has something in common. Here's what I'm going to try to convince you. Follow this logic and then I'll get into the details. I'm going to try to convince you that if you went home and you had a way to determine this, whether two given context-free languages had something in common, yes or no, if you had a way to do that, then I'm going to show you how to use your method to solve this problem. And we know we can't solve this problem. It's impossible. So if you have some hypothetical method, and I can show you how to use that method to solve this problem, that means you don't have any hypothetical method. It means you're lying. Right? So I'm going to show you exactly that. I'm going to show you that if you had a method, how could you use it to solve this problem? And because of that connection between the solution to this problem implying the solution to this problem, it means this problem is undecidable. What this means technically is that we are reducing the PCP problem to this, we'll call it empty intersection problem. Intuitively, I'm showing you that the empty intersection problem is at least as hard as the PCP problem, because if you could solve the empty intersection problem, I will give you a way of solving the PCP problem. And since PCP is undecidable, and this is harder, or at least as hard as undecidable, then you're in pretty bad shape. So how am I going to connect the PCP solution to being able to solve this problem? This takes a little bit of a leap. And once you see it, it'll make a lot of sense. It's not, like I said, it's not way out in the middle of nowhere. So here's what we're going to do. Somebody's got a PCP problem. Let's pick one. How about this one? As good as any. Somebody gives me a PCP problem. I'm dying to solve it. I know somebody who's got an algorithm for this. So here's what I do. I'm going to take my PCP problem. I'm going to fiddle with it to come up with two grammars. I'm going to give it to my friend who's got an algorithm for this. And if they tell me the answer to this is yes, I'm going to know the answer to the PCP problem. If they tell me the answer to this is no, I'll know the answer to the PCP problem. So here's what I'm going to do. I'm going to take my PCP input, I'm going to fiddle with it, create 2 grammars, and hand it to this person, and let them do their work. And I'm going to convince you there's a relationship between the answers. Okay, questions about that process? That process is called a reduction. You've seen it before in other ways, in algorithms, but now we're doing it here with grammars. Here's the grammar I'm going to come up with from this example. Looks like this. Look at this grammar for a minute and get used to it. What kind of things does this grammar generate? It's a grammar that comes from the A column of my input. What does it generate?
Are the little letters terminals or non-terminals?
The little small letters are always terminals. So the A, B's, and C's are terminals. What kind of things does this generate? It's got bunches of 1s and 0s followed by collections of A, B's, and C's, right? The 1s and 0s represent concatenations of these strings, right? And the A, B's, and C's represent kind of a record of which strings were concatenated. For example, if you see an A, the first thing right after the 1s and 0s, that means the very last sequence of 1 and 0s was this 1. If you see a B, it means its matching sequence was a 1, 0, 1, 1, 1. It's a way of remembering the order of the strings and how I generated them. For example, 2, 1, 1, 3. Let's actually do this one. 2, 1, 1, 3. We end up getting 1, 0, 1, 1, 1. Then there's 2 1s, so it's 1, 1. And then there's a 3, it's a 1, 0. What does the right side look like? The A, B's, and C's that get generated by this grammar if we concatenate 2, 1, 1, and then 3. C, A, B. Okay? I can match these up. Here's the C. That's the last substitution I made. Here's the A. Here's the A. And here's the B. That's the kind of things this grammar generates. Concatenations of these strings and keeping a record of where they came from. This is like the sequence, the 3, 1, 1, 2. It keeps it in reverse because it's all nested. Questions about that? If you get that, fine. If you're wondering where we're going with it, you'll find out in 2 minutes. But just make sure that makes sense, because we're going to do the same thing now with B. So this looks like 1, 1, 1, SBA. 1, 0, SBB, and 0, SBC. Same kind of grammar. Now let me ask you a question. Can SB generate that string?
Yes.
Right. Erica told us how. SB can generate this string by starting off with what production? Starting off with 2, with this second production, and then doing this twice, 1, 1, and then doing this, 3. And you get the exact same sequence. This would match up because we checked that it matched up before, and the CAAB would match up, showing that we actually did. What does that guarantee? That guarantees that we picked these in pairs like we're supposed to. If we made these grammars without the C's and the A's and the B's, then getting a match wouldn't imply that we solved the post-correspondence problem. It would imply just that we mixed these any way we wanted. So we want to make sure that we pair these up right. All right, well, fine. So this generates strings, and this generates strings. If these two generate the same string, it implies that there's a solution to the post-correspondence problem. I can just use this sequence. And I'm going to get the same string in grammar A and the same string in grammar B, and I can connect that to a solution to my post-correspondence problem. So I give this grammar and this grammar to my friend who knows how to check for empty intersection. And I say, do me a big favor and tell me if there's any string in common between these two. And they go home with their hypothetical empty intersection algorithm, and they churn and churn and churn, and they come back the next day and they go, yeah, here it is. Here's a string that they both have in common. They do have something in common. Here it is. Then what do I say to my post-correspondence problem? I say the answer is yes, there is a string that you can concatenate the A's and the B's together. What if they go home and they say that they have nothing in common? There is no possible string you can generate from SA that matches a string you generate from SB. Well, if you think about SA generates every possible combination of sequences from column A, and SB generates every possible sequence of combinations from SB where the sequences match. So if they have no strings in common, then there's no way at all to solve this problem. We just went ahead and took the post-correspondence problem and hid it inside these two grammars. And now my friend who knows how to check whether there's empty intersection between two context-free languages can solve the post-correspondence problem for me in this backhanded, sneaky way. And all I have to do is this little reduction. I got to take my post-correspondence problem, create these two grammars, hand it to my friend, get the answer, and send the answer back to the person who wants the answer to the post-correspondence problem. That's a reduction. The reduction is the changing of the input of the hard problem to the input of the unknown problem, and showing that the answer to this is true if and only if the answer to this is true. And that's what we've been doing in this discussion. Any questions about that? That's the first undecidable problem. So you can't do this because it implies that the solution to this and this is impossible.
You have to avoid the trivial point that they both generate epsilon.
Oh, yes, right.
So it's like a null. We're asking for a null set, not the set. It's just
Right. I guess that would, the person would always come back and say, oh, yes, they always have something in common, epsilon. I have to ask them if they have something in common besides epsilon.
since you're paying them to do something.
Yeah, right. Right.
And you could build that so that epsilon wasn't a possibility, that you had to have.
That's true. In fact, you know, the epsilon is really, I really shouldn't have these epsilons here. I really should have
You should have an SA1 or an SA2.
I could get rid of this epsilon. It's a technicality. Todd's right. The way I have it now, it's not quite right. I need to make these epsilons real terminal symbols, but I could do it. I need to, here, it's not so hard to do. Instead of the epsilon, I need to put in 1 small a, 1 0 1 1 1 small b, and 1 0 small c. I just need to put those out explicitly instead of the epsilons. There shouldn't be epsilons there. I should maybe fix it. 1a, 1 0 1 1 1 b, 1 0 c. Same kind of thing here.
That puts,
Isn't that okay?
no, because then you'd be putting the number at the end, like the letter. You'd be putting numbers at the end of the number string and the letter at the beginning of the.
No, it's okay.
Oh, is it?
I think it's okay.
Backwards that way?
Yeah, they're always throw backwards. Yeah, that's perfectly fine. Essentially what I just did is get rid of the e productions, because I really don't want the e productions. And I could do the same thing here. And it's a good point. Technically it was really wrong before. All right, questions about this? Okay. Let's do another one. These grammars are kind of famous, so it's the bridge between PCP and grammar problems. But now that we've got this grammar problem that's undecidable, we're going to milk this for everything it's worth, and I'll convince you that another grammar problem is undecidable. And then they're all just going to fall like pins, and they're all going to be hard. All right, so let's consider this problem. The problem of L being equal to everything. You go home and you've got a way to check whether L equals everything. And I'm dying to figure out whether two context-free grammars have something in common. I'm going to show you how to solve this problem if you know how to solve this problem. So I'm going to reduce this problem to this problem. PCP reduced to this, and I'm going to reduce this down to this. How do I do that? I'm trying to solve this problem using this as a subroutine, basically. Right? That's what I tried to do here. I tried to solve PCP using this as a subroutine. And I assumed that there was some solution to this, and I showed you how to do it, and then I know that there's no way to solve this, therefore that subroutine can't exist. So same thing here. I'm going to show you how to solve this if you know how to solve this problem. How do I do it? Here you can make a good guess. Here you don't need this jump for a fancy grammar. How do you check if the intersection of two languages is empty, if somebody can tell you if a language gets everything? Let's try something and see if it works. That's the way to try, but when we tried to use complement before, why couldn't we? Why can't we just complement L and check whether L complement equals empty? We know how to check whether a context-free language equals empty, right? So why don't we just take the context-free language we get, complement it, check for empty, and then if that's empty, that'll tell us our original is everything. Well, how come that doesn't just show that this is decidable? It's because when we take the complement, we don't get a context-free language necessarily. We might get a Turing machine. And it is not possible to check whether a Turing machine accepts nothing. That's actually undecidable. So that doesn't work, that idea. Well, let's kind of use that idea here because you get this really cool connection of closure properties that make it just work perfectly. Here's what I mean. Somebody knows how to solve this problem. Here's what I'm going to do. I'm going to take this intersection, and I'm going to take its complement, and I'm going to give that to them. And if they tell me it's everything, then I'll know the original was nothing. So my first step is just take the complement of this. Take L1 intersect L2 complement, and give that to the person who knows how to check for everything. And when they say yes, I'll say yes. And if they say no, it's not everything, then I'll know that the original is not nothing. Well, what's the deal here? I just took two context-free languages, I intersected them and took their complement, and I'm implying that I'm resulting in another context-free language. So it's completely unfounded. You can't intersect two context-free languages and get a context-free language, and moreover, you can't complement them and expect another context-free language. Nevertheless, interestingly enough, I'm going to convince you in 2 minutes that this is definitely a context-free language. It's kind of like two wrongs will make a right. Here's how I'm going to convince you. Let's look at L1 and L2 because they're not just arbitrary context-free languages here. Actually, you remember where they came from the PCP? There were very specific kinds of languages that this problem was hard for. What do they look like? I'll write it down again. Here's an SA, right? SA goes to 1 SAA, 10111 SAB, and 10 SAC. And then 1A, 10111B, and 10C. Look at this language. Look at this grammar. If you had to make a machine for that, could you make a deterministic one, or do you have to use non-determinism? How would you make a machine that accepts the strings generated by this grammar? What would you do? Let's talk about that for a few minutes. Because what I want to convince you is that these two languages here can be assumed to be deterministic. And if they are, I'm going to be able to convince you that that's going to be a context-free language. But let's think about these languages and make sure that they're really deterministic. What method do we have of coming up with a machine that's going to generate the strings that's going to accept the strings that this language generates? How do you want to do it? Here's a possibility here. You're reading through the string. What are you going to do? What are you going to do with these ones and zeros? You got a push-down machine at your disposal. What do you want to do? What if we look at these symbols and throw them on a stack? Okay, as we look at them, we'll just put them on a stack so we have them stored up. And now finally we get to the C. And I have my machine in some state say, hey, if I see a C, I'm going to go into a short little loop of 2 states long that looks for a 0 on the stack and then a 1 on the stack. And I'm going to pop them off. And then I'll move on and read the next symbol. If I see a C, there's got to be a 0 and a 1 on the stack. That's the only way you could possibly generate a string, where there's a C here in the middle. So you push all these symbols on your stack, and then you read through the C's and the A's and the B's, and you program your machine so that when it sees a C, it goes into a 2-state loop that looks for a 0 on the stack and pops it, looks for a 1 on the stack and pops it, then comes back, and then it reads the next symbol on the tape. If the symbol's another C, it goes through the same loop, hoping to pop a 0 and a 1. If the next symbol's an A, it's going to pop a single symbol 1. If the next symbol's a B, it's going to go into a loop of 5 states long, which will pop 1, 0, 1, 1, 1. It's a finite machine. It's a deterministic machine, and it uses 1 stack. So every one of these grammars, no matter how long the strings are, no matter how many of them we have, A, B, C, even all the way up to Z, you could go home and write a deterministic machine for them. If you're not sure you can do it, I'll add it onto the problem set next time, and then I'll have to force you, and then I'll help you do it. But it wouldn't be so bad. I could give you this, and I'd say, make me a deterministic machine that does this. It isn't too bad to do. You could also turn it to Chomsky normal form and convert it, but that would be non-deterministic. So you don't want to do that. You want to just think about determinism. Put this in the stack and then pop them off deterministically. There's never a choice what to do. Either it's going to work or you die. Or Sharon, you look like you're trying to figure it out and it's all confusing.
I guess I understood what you just said. I guess I'm just furrowing my brow over how we got from L1 intersects L2 must be in the form of a grammar like the one you just said.
Oh, well, because, don't even think about it. I'll just go back to PCP to begin with. I know that PCP is undecidable, so I want to solve it. And in order to solve it, I'm going to come up with these 2 grammars again. And then I'm going to intersect them and take their complement and give that to somebody who knows how to check whether a language is everything. So I can assume it because I constructed it myself. I came up with it. So I know that these 2 languages can be deterministic without any loss of generality. I don't even need this intermediate step. You can even forget about it. I'll just take these 2 languages, intersect them myself. Should we write this machine, or can you do it? Is it boring to write it, or should we write it? It's not that long to write. It's about a few steps. Let's write it. It won't take too long to write. And then maybe it'll take the mystery out of it. Where's a good place to write it? I'll get rid of the no instance here. Let's write it here. It starts here. If it sees a 0 or 1, it just pushes it on the stack. So 0, anything, push it. 1, anything, push it. Okay, it pushes the 0s and 1s in the stack. Sooner or later, it gets to see an A, a B, or a C. Okay? So I'll say A, B, C. Doesn't matter what's on the stack, right? Is that okay? Can I have this all in one arrow? I want to do different things depending on whether it's A, B, or C. If it's C, I'm hoping to pop off a 1, 0 from the stack. If there's no 1, 0 on the stack, I don't want to accept it. So I got to make 3 arrows here. A, B, C.
Why can't you do that with one? Oh, because you can't throw it away. Never mind.
I can't throw it away, right. I can make an E move, right. All right, so if I see an A, what should be on the top of the stack?
All right.
The only thing A can generate is a single 1. So there should be a 1 on top of the stack. And what do I do with it? I pop. And then I go into a big processing state to process the rest of the A's and the B's and the C's. If it's a B, what do I do?
Go through a 5-state chain. And
Right, I go through a 5-state chain where I pop off 1, 0, 1, 1, 1.
11101.
11101. Right, I need to pop it off in reverse. So this is a long chain, and when I'm done popping them off, I go into the processing state. Right? So that means I saw a B, and the symbols that a B could generate were there. So I matched up, and things are fine. And if I see a C, I have something that is 2 symbols long. So I need just 0 is the first one I pop off. 0 pop, and doesn't matter, nothing, 1 pop. Don't look at anything, and pop the 1. And now I get to this state, and I just have these same kind of things, 2 long loops, 1 for A, 3 long loops, sorry, 1 for B, and 1 for C. The 1 for C is 2 long, the 1 for A is 1 long, the 1 for B is 5 long. And I keep processing and processing and processing A, B's, and C's until sooner or later the stack is empty. There's no more 0s and 1s there. We ate all these up, and there's no more A, B's, and C's to generate them. E, Z, Z, and we accept. So it more or less looks like that. I didn't do every detail, but I did a lot of the details. It isn't too complicated of a machine, and it's definitely deterministic. There's no choices to be made at any point along the way. All right, maybe that helps, maybe it doesn't. If this is confusing, just take my word for it that these are deterministic languages. And if you get it, good, and if not, take my word for it for now. I'll leave this for now. Let's get back to here. So I want to solve the PCP problem. I know somebody who's got a way to do this. I make my 2 grammars. I intersect them. I take their complement. I give it to the person who can check if that complement is everything. If they tell me it's everything, then I know that the intersection is empty. And if the intersection is empty, then I know there's no solution to my PCP problem. Chaining right through all these logical steps.
We don't have closure.
Let's talk just about that. That's the last thing to talk about. I have to convince you that this really ends up being a context-free language so I can give it to the person who has this alleged algorithm. Let's see what happens here. L1 intersect L2 is something, and taking the complement is something that I keep telling you is going to be a context-free language. How do I know that? Let's rewrite it. Here's the coolest trick. This is De Morgan's law, right? So this equals this. So here's what I'm going to do. I take my L1 and L2, which I know are deterministic, and I complement them. Therefore, they are still deterministic context-free languages. Then I union them. Are they deterministic context-free languages now? No, but they're context-free because the union of 2 context-free languages is context-free, and every deterministic context-free is context-free. So there's 2 closure things here. The complements stay deterministic context-free because deterministic context-free languages are closed under complement. The union of those 2 stays context-free because context-free languages are closed under union. So I take this, and I give it to the person who can check if it's everything, and I'm guaranteeing to them that it's a context-free language. And then they can tell me if it's everything. And if it is everything, then I know that this is nothing. And if this is nothing, then I know there's no solution there. If it wasn't everything, then I know that this is something. And if this is something, then I know there's a solution to that. So I can get all my answers trickling back. Only if somebody knows a way to do this. But I can't get any answer to this. That's impossible. So this long, clever method I have of connecting these 2 problems serves to show nothing more or less than this problem is just as hard. That I can't really do this. Does it show that this problem is hard for deterministic context-free languages? No, this problem is easy for deterministic context-free languages. And the reason it doesn't is because when I union these together, if I got a deterministic context-free language, that would really show that it's hard. But I don't. When I union two deterministic context-free languages together, I don't get a deterministic context-free language. I get a bigger language. I get just a regular context-free language. So this is not enough to show that the problem is hard for deterministic context-free languages. It's enough to show that the equal sigma star is hard just for context-free language. Right, that's the second example today, and maybe the second hardest. We have a few more to do, and the rest are much easier. Are there questions about this? Remember that at the heart of all this is proving the very first problem is undecidable, and we haven't done that yet. I want to do that kind of at the end because it's the most magical. This stuff is very constructive. There's no magic here. If you really go through it slowly, it will make complete sense. There's nothing tricky. You can really do these constructions. But Cantor's diagonalization, that really is magic.
We're not going to talk about the connection between diagonalization and post-correspondence stuff.
I'm not planning on it, but it is a good possible topic to do. It's very technical and hairy. And it's probably in the book, although I didn't check for sure.
What, showing that's undecidable?
Chris is asking, right, Chris is asking, are we going to talk about the relationship between the halting problem and the post-correspondence problem, which basically takes an arbitrary Turing machine and turns it into pairs of strings so that those pairs have a solution in the post-correspondence problem if and only if the original Turing machine does an infinite loop. So you can imagine the technicalities involved there, and it's a little ugly, but it's not terrible conceptually, it's just terrible technically. Okay, some more problems. Somebody gives you a grammar, they want to know whether it's ambiguous or not. Say you had a way of checking whether a grammar was ambiguous. Yes or no, you could tell me. I can solve the post-correspondence problem. I make these same grammars, SA and SB, and I make a new grammar called S goes to SA and S goes to SB. And I give that to you, my ambiguity checker. Now this grammar is going to have two different parse trees for the same string if and only if SA and SB can both get that string. If they can both get that string, we get two different trees for the same string. And if they can never get the same string, then all the parse trees are unique, and the grammar is unambiguous. So all you got to do is do this one little trick and give it to an ambiguity person, and if they can solve it, you can solve post-correspondence problem. That's an easy reduction, relatively speaking. Here's an even easier one. What if I give you a context-free language and I ask you, I give you a grammar, it generates something, and I ask you, hey, does this happen to be a regular set? Could you have done better? Could you have made a finite state machine for this? Did you really need the deterministic pushdown machine that you used, or the context-free grammar? Is it really a simpler language? I give you a context-free language, is it also a regular set? Do you think that's a hard problem or an easy problem to decide?
Isn't determining whether something's a regular set an easy problem?
You give me an arbitrary set, I have to decide if it's regular or not? That's not an easy problem.
No. Okay, no.
Here I'm giving you a particular context-free language, and I'm asking you, is it regular or not? All right, so say Heather's got one. She's got a method. And if I give her a context-free language, she'll plug it into her program, and it will tell me if it also happens to be a regular set or not. All right? So I go, great, Heather, do me a big favor, and tell me if you can solve this problem for me now. I want to know if a given grammar generates everything. So why don't I just go ahead and give you sigma star, and you throw it into your check if it's equal to a particular regular set, and if it says yes, then I got my answer to this problem. So if I ask you, given a context-free language, is it equal to whatever, 0 star 1 or anything, and you can solve that problem, you can certainly solve whether it's equal to this. So that's just hard. Showing whether a context-free language equals a particular regular set is hard. because it's hard enough just to do this one regular set. What else? One or two more, and then we'll quit today. L1 equals L2. Hard or easy?
When you're saying hard or easy, we really have to be thinking possible or not possible.
Right. Is it decidable or undecidable? I give you two context-free languages. They generate the same thing or not. It's not possible. How do you know it's not? If you could do this, what else could you do? If you could take any two context-free languages and tell me whether they were the same, what other one of these other undecidable problems that we talked about today could you also solve? The empty intersection? How would you do that?
Well,
Oh, I don't think that connects exactly. There is another one that connects much more precisely. You might be able to fiddle with that a little, but I don't think it's going to work precisely. If I can take any two context-free language and tell you whether they're equal, then I can certainly take video guy. Did you say what I could do? Right, I could certainly just take one context-free language and sigma star, which is a context-free language, and check whether those two are the same. And we know we can't do that. So there's certainly no way you can do this. This is harder. This does that and more. Those are called reductions by restriction. They're almost trivial reductions. This is just a generalization of a problem that you already showed me was too hard to do. This is already hard. How are you ever going to do this? As long as sigma star is context-free. Other examples. One language contained inside the other. Same trick. Let's make this language sigma star again. If you had a way of checking whether one context-free language was contained in another, then I'll give you sigma star as the first language and ask you if it's contained in any other language. And then I'll find out if it is or if it's not, whether this language equals sigma star. Because if sigma star is contained in it, then it's equal to it. And if it's not contained in it, then it's not equal to it. So again, it goes back to being able to solve this. So contained in, equals, all this stuff, you can't do any of it. Ugh. It's so hideous. Somebody gives you a regular set, asks you whether it's contained in a context-free language. Same exact reason as before. Somebody gives you a finite state machine and says, is everything in this finite state machine accepted by this pushdown machine? The answer is no, because all I have to do is give you a finite state machine that accepts everything. And if you had a way of saying whether it was contained in an arbitrary context-free language, then you would have a way of saying whether that arbitrary context-free language equaled everything. Because everything being contained in a language is the same as it being equal to it. So this is impossible. All undecidable. But now that I'm throwing all these undecidable at you, and you say, oh, everything's undecidable, everything's undecidable. So then there's always like the trick question. Somebody gives you a context-free language and asks you whether it's contained inside some regular set. Okay, I'm giving you two things. A finite state machine, a pushdown machine. I'm asking you, does that finite state machine contain everything that this pushdown machine generates? Now I can't do the trick I did before, because if I throw sigma star in for this guy, that's just that's not a difficult problem to do, to check whether regular sets are equivalent. It doesn't help me solve this problem. It only helps me solve this problem when I have a context-free language that's on the right side. But I know how to solve the problem whether R equals everything. So maybe I can really do this. Maybe this isn't undecidable. Let's finish with this today. Let's figure out a way to do this. This can be done. You can decide whether a context-free language is a subset of a regular set. Let's see if we can figure out how to do it, and we'll quit here. try kind of the standard thing, the thing that we did before when this kind of thing came up with regular sets. How do you convert this to set operations? You did this last time, Heather, right? Do you remember? What's it the same as? L1 is a subset of R if what? Think of this as implies. So if it was A implies B, it would be not A or B. So it would be like not L1 union R equals everything. I'll write this out. Not L1 union R equals everything. And that's the same as the complement equaling nothing. And that's the same as L1 intersect the complement of R equaling nothing. L1 is a subset of R. Here's R. Here's L1. L1 is a subset of R if the intersection between L1 and R complement is empty. Okay? If there's nothing that comes out of here. You can make a Venn diagram. Maybe it's easier to see than the discrete math way. But these two are equivalent. What is this? R complement, is that regular, context-free, not context-free? What is it? R is regular, so R complement is regular. L is a context-free language. We talked last time that you can intersect a context-free language with a regular set, because you only keep track of one stack, and the states just become products. So when you intersect a regular set with a context-free language, this becomes a context-free language. And this ends up being a problem that is checking whether a given context-free language is empty. And that you can do. So keep your mind open to these problems. It's very easy for someone who does these a lot to convince a beginner that a problem is undecidable when it's really decidable, and that a problem is decidable when it's really undecidable. You have to be very, very skeptical. Don't believe what anybody says, even if they're your friend. Nothing I said in this lecture was actually true. No, you can trust me during the lecture. But as far as, you really should be very, very skeptical. You're going to read things now that's going to be on the cusp of, yeah, I think I'm getting it, but if somebody threw a monkey wrench in, it could squeeze by. And try to be very, very, very harsh with your critique of when somebody's giving you an argument along these lines. These things can get very tricky. Dimitri's philosophy about this, he tells me, he goes, when things are finite, everybody can get it. That's how he talks. Everybody, there's no problem. They get it. But when things are infinite, it's just, you know, you get confused. And I never thought about it that way. To me, everything seems confusing unless you think about it for hours and hours and hours. But maybe he's right. Maybe just when you get into this world of the undecidable and the infinite, you feel like you're walking a thin line. So be very, very careful. Don't feel you have to get vague. Everything we did today was completely constructive and completely checkable step by step. We did it fast, we did it intuitively, but there's nothing lacking in rigor with anything we did. And everything we showed as undecidable is really undecidable. Everything we just showed is decidable. You can write a program to do it. All right, so this is the bridge between context-free grammars and Turing machines. We'll start with Turing machines next class, the next level over. We'll talk about Alan Turing's original paper when he described his motivations behind what makes a Turing machine, try to give you a sense that intuitively a Turing machine is like the programs you write. It's an unrestricted form of computation, just like the programming languages you use. And it pushes us up another level. All the sets that we couldn't get before, now we're going to be able to accept them. The only sets that we can't accept now are the things that no computation can accept, are the things that are undecidable. The only things that are out of our frontier now are these undecidable things. And I wanted to do the undecidability now because I think it's more important to see it now. Later on, it's going to seem more magical and diagonalized and weird. And you need to see the connection to context-free languages now rather than come back to it later. Okay, so let's quit here. And any questions, I will answer them after class.